Hi, I'm Rucha. I'm from Nizer, Bhubaneswar, India. I'm going to give an overview of my work that I'm doing currently. So, as you can see in the title, it's about the privacy in graphs and the graph generations also. So, yeah. So let's just recap through how graph neural networks works. So as we know, there are nodes in the graphs and edges, and we can see XV that we see here are the features of the nodes. So those are the layer 0 embeddings of the nodes, and we want to generate in GNN, we want to generate some embeddings for the nodes, and then we can pass them to the downstream tasks to answer whatever question we are aiming at. So in order to generate the kth layer embedding of for the node we take its previous layer embeddings, and we also aggregate the neighborhood of the node. So this is something that we are interested in later slides. So, and then we have, of course, non-linearity applied to it. This is in one layer of GNN, and later we apply multiple layers of GNN, and we generate the embedding for that, which we can pass later to the downstream tasks. So this is the basic idea how a graph neural network works. And talking about the privacy in graphs, we saw how graph neural network work previously. So imagine a network where we have nodes that represent users, and of course they have connections between them. And but the users have the private information. So as we can see in this example here, the age and the salary of the user, it's something that the users may not want to share with anybody. They want to keep this information private. And in addition, they also want to benefit from the task that the GNN is addressing. So the idea is the GNN should perform nicely. At the same time, we want this private information not to be leaked to anybody. So that is the idea. Now, as we know, the structural information is also important in addition to the feature information in the graph. So we saw in the previous slide that every node in the graph has a feature vector associated, which is the feature information, of course. And in this graph, we can say age and salary. And we are aggregating the information over the neighborhood, which means the structural information is also important. So the previous works at the time when we were doing this work, all the previous works majorly were based on privatizing the feature information, whereas nobody looked at, or it was nobody looked at the structural information also. It's very important to, as we are aggregating over structure, we may not want to disclose who our neighbors are, right? But we also want to get the good accuracy. So that is what the motivation is. And what we proposed was how we can privatize the neighborhood information. So this node feature information is privatized using a multibit encoder, and it's rectified using multibit rectifier. And then they apply k-prop onto that. K-prop is basically a GNN layer without any non-linearity. So we just aggregate over the neighborhood, and then it is passed to a GNN. So user share their privatized information, user adds noise to the information, and then share it to the server for the GNN to be applied at server side. Similarly, the labels of the nodes are also privatized using a mechanism called randomized response, where with some probability the bit is flipped. Now, this was the previously available work. What we contributed was we were proposing the method to add noise to the neighborhood. So here, as you can see from this slide, there is a lambda selector. Lambda selector is basically what we do is we select lambda percentage of the neighboring edges, and we apply randomized response onto that lambda percentage of the neighborhood, and then randomized response leads to addition or the drop in the neighborhood edges that we have selected. So that basically adds noise to the neighborhood, and that is the point. So once we have this noisy neighborhood information, this and this is done at node, locally at node. So the node shares this noisy information with the server, and we are limiting it by lambda. So as the lambda increases, that basically adds very more noise to the neighborhood information. Then we pass this noisy neighborhood to the server, and at the server side, to compensate for the added noise, we again apply kprop, which is again, as I told earlier, it's the GNN layer without a non-linearity. So we aggregate over the neighborhood and then use and apply the GNN. So what we found was, as we expect, as we increase the value of lambda, more and more noise is added to the neighborhood, and that leads to drop in accuracy. Also, that we also should note that that adds privacy to the data of the user. So there is always a trade-off between privacy and accuracy, and we see the results as expected. As expected. So this was about the privacy part. So there is some other work also going on, I mean, submitted somewhere, so not discussing here as of now. And then the other problem that I'm also working on is of graph generation. So basically, currently we see a lot of graph generation paper published at many venues. So what is a good generative model is something that I'm looking for, or these are basically the goals of the graph generation problem that I'm looking at. What metrics define the distribution from which we can sample the graphs, and how can we learn the underlying distribution is another question. And what is the okay, so in the matrix that we determine, do they score good is also the question. And some of the properties that I'm looking at is expressivity, scalability, permutation invariance, and novelty. So we see a lot of graph generation papers currently, and most of them are for the simple graphs or single layered graphs. But I'm looking at multi-layered graphs, where basically a layer in the graph is a subnetwork, you can say. They have interlayer edges and also across the layer edges. So that is the generation problem that I'm working on. And that is about my work. And if you, for more information, you can visit my website. And if you have any questions, I'm ready to take. Thank you.